Hello. 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 Hi. Okay. Hello, everyone. I am Josh Fitzgerald. I'm from ANOMA, and I'm going to present to you Vamp-IR. It's a language for arithmetic circuits. So, first thing is why make a language for arithmetic circuits? The answer is it's a big pain to write circuits. We have DSLs, which can help with this, but DSLs are often highly tied to a specific proof system or backend. And if you want to change the proof system that you're using or change the backend library, then you often have to rewrite the circuit essentially from scratch. And it's challenging. If you're like me, you might find it fun to just mess around with polynomials and try to figure out if they're equal and things like that, but it's not a very efficient use of time. At ANOMA, we have a multi-asset shielded pool. That's the MASP here in the middle. And it was written for Grow at 16 in the Bellman library. We wanted to extend or convert that to another proving system like Planck. So I spent some time trying to do this. I read the spec for the MASP and tried to translate by hand all the polynomials into Planck library. And once you do that, you're left wondering, did I do that correctly? Did I make a mistake? Did I leave out a critical constraint somewhere? The worst thing that could happen if you're writing a circuit is that it's under-constrained, and there is some satisfying solution to that circuit that shouldn't be there. And it's hard to tell when you're working with complex circuits if you've done it correctly. Also, have you done it in an optimal way? It's really difficult. So why don't we have a language for arithmetic circuits that can represent an arithmetic circuit canonically and universally, so that that same circuit can just be ported to whichever library you want to use. And then all you need to do is write a compiler from this language to the backend library, and it takes care of transforming it into a form that those libraries want. So that's the basic idea behind Vamp-IR. On the other side, you can write DSLs that compile to Vamp-IR. So at ANOMA, we have some languages that are going to do this. We have Juvix and Alucard. Juvix is our dependently typed programming language for validity predicates, and it will also create an arithmetic circuit that represents those predicates. Alucard is a Lisp-like tool for writing circuits. It's going to have some helpful gadgets like SMT solvers and things like that to make writing circuits easier. And there's no reason you couldn't write a compiler from, say, Socrates or Circom, those languages into Vamp-IR as well. And then on the other side, you can change Vamp-IR into R1CS or Planckish constraints. And then if you need to refine it further for a particular library that you're using, you can do that as well. All of these arrows are compilers. So what started as a cryptography project has now become a compiler project. And we've got a great team of compiler experts who are working on this now. So let me show you how arithmetic circuits can be represented. Here are two arithmetic circuits. I drew them like they're printed circuits. It's a really good analogy for what they actually are, because you have these different nodes, and they're connected by wires, and you can apply a signal to these nodes at the top. You could also wire two nodes together, and that means that those will have the same value. So imagine applying a voltage somewhere. If you have a wire connecting to another node, that node has the same voltage, I guess. I'm not an electrician. I don't know if that's actually true, but so yeah, here's our two circuits. An arithmetic circuit is just a representation of the computation of a polynomial. So here we have actually the same polynomial twice. This side is the factored version. The other side is multiplied out. Two very different looking circuits. They represent the same polynomial, but the order of computation, the computational steps are different. Over here you add two pairs of things and then you multiply. On the other side you multiply like 4 pairs of things and then add them all up. All right. Oh yeah, this is what I was saying earlier. You can take two circuits and join them together by drawing wires across. What this lets you do is treat a circuit like a function. All you have to do is specify the inputs and outputs of the circuit. And then when you compose two circuits, the compiler will know how to handle those inputs and outputs. It will make sure the inputs of the outer function match the outputs of the inner function, you know. Also, this wiring here is what you would actually need to do if you wanted to do modular. If you wanted to find the remainder by dividing by 16, you would have to do this. Calculating the remainder is easy. It can be done here, but you need to make sure that the remainder isn't too big. Right? So then you have to use a range proof on the other side. So this is actually what you would do. An arithmetic circuit defines a system of polynomial equations as well. So there's our system of equations on the right side there, along with that range 4. It's a 4-bit range circuit here. Okay. You can also represent an arithmetic circuit as an expression tree. It's because an expression tree is just polynomial if you have addition and multiplication. So there's another representation here. All right. You can also represent an arithmetic circuit as a kind of flat list of gates and wires. So we have 5 inputs. It's for Z, A, B, C, D. And they each have an index, and then you can list the operations. We're multiplying 1 and 1, that's A times A. Mul 2, 2 is B times B. So we're getting A squared and B squared and so on. The box on the far right, those are equalities. If you are saying the gate at index 11 is equal to the gate at 0, you're drawing a wire. That is basically, that's this wire here. Okay, so sometimes you need extra equalities to get all the wires in the right spot. That's what those are. Okay. So I want to give an example of what it would look like to write a circuit in Vamp-IR. Now that we know what circuits are, I think you can kind of see how this will work together. Vamp-IR uses something called an alias. It's just a definition that takes some expressions. These expressions define a circuit, and it also gives a signature to that circuit, just like a function signature that allows that circuit to be composed with other circuits. Circuits don't have like a natural composition, but if you can specify inputs and outputs, then you can do it. Okay, so here are some definitions. This top one here, def bool x, this does not have an output, it just has a single input, x, and it checks that x is 0 or 1. It does that by multiplying x by itself and making sure that those are equal. 0 and 1 are the only solutions to that polynomial equation, so it constrains x to 0 or 1. This 4-bit range function here, this is for showing that x is less than 16. You can use another alias inside of a definition, just like this. So this is a squared equals a, b squared equals b, and so on. And then at the end, you pack those bits together and constrain them to be equal to x. Okay. On the other side, I have 3 different aliases, but the circuit is the same. So it's like the same circuit board, just with different nodes selected or designated as inputs and outputs. So if you want to do mod xy, then you want to return r. If you want like integer division, then you return q. If you want div mod, like they have in Python or whatever, it can return the pair qr. Same circuit, just different signatures. Okay, so this is a tiny circuit which could be used for like an educational game. In this game, a player submits a triple of numbers, and they're supposed to receive a score of 1, like a point, if that triple is Pythagorean. So in like a zero-knowledge context, what the player would have to do is submit their triple and the score that they claim they should get. And then a verifier could check this in zero knowledge that the score is correct given the triple. Okay. So a verifier needs to check that if a squared plus b squared equals c squared, then the score should be 1. And if a squared plus b squared is not equal to c squared, the score should be 0. Okay, so I have 2 aliases defined to do this. The top one is Pythagorean. This checks that x, y, and z satisfy the Pythagorean theorem. The middle one there, it might be a bit hard to parse exactly what's going on, but what that is going to do is check if x is 0, then the bit should be 1. And if x is non-zero, the bit will be 0. You can think about the cases there. Just do like a case analysis, and you can see that it works out. And finally, at the bottom, we have the actual circuit. We just say S, the score, equals is Pythagorean ABC. So if the Pythagorean circuit is satisfied, then the value in the parentheses there will be 0. And then the is circuit should output a bit that is 1, which is the score. If the Pythagorean circuit is not satisfied, then the value there in the parentheses is non-zero, then the is will spit out a 0 for the bit, and the score will be 0. Okay. All right. I'm running out of time, so I will breeze through these compilation steps. This is an example compilation steps here. We have, like I said, we have a team of compiler people who are taking over this portion of Vamp-IR. I think they're going to change and improve this, but this can kind of show you how to get from a Vamp-IR circuit that's actually written in Vamp-IR to, say, a Planck circuit. So the input is parsed and put into an abstract structure tree like this. Got the definitions on the left, the actual circuit on the right. You can put this into an ANF form where you have inputs at the top of the list. Then you have your functions, your aliases, and so on. All right, you can expand this. Pythagorean and is, they have polynomial equations defined inside of them that you can replace those with. So you can expand like so. You can make some little optimizations like the equals at the bottom, 10, 14. That's unnecessary because 14 is an input. 10 is also an input. So there's no reason to ask the prover to input two numbers that are the same. You can just use the one. You know, why not? You can do things like change subtractions to additions using constant multiples, things like that. And then you can Planckify it. So I'm calling this 3 Planckification because it's using like 3-wire Planck. And you can kind of see that there's almost parity here, but we end up with one less item in our list of Planck constraints because two operations, I think it's 11 and 12, can be combined if you're using a Planck gate with 3 wires. Okay. So we have some interesting, promising directions that we're going to do some research on and incorporate into Vamp-IR if possible. One is tools from algebraic geometry, ideals, varieties, Grubner bases. There are some things there that can be useful for showing that two circuits are the same, for instance. SMT solvers, which can also help show that circuits have certain solutions. Stark circuits. Starks use circuits as well as snarks. They're a little bit different, but we can use Vamp-IR to represent those circuits as well. And category theory. Cartesian closed categories compile to polynomials, apparently. We just started talking about this recently. So we may be able to compile from Juvix to Vamp-IR in a different way using this fact. Very interesting stuff, very new and preliminary, but very cool. Here's our Vamp-IR team. I'm really excited that we have these people working on it. I think they're going to do a great job. So, thank you. Yeah, it's open source. You can find it at Anoma, our GitHub. Look for Vamp-IR. It is not usable yet. We are working hard on our tree, our abstract, our AST, and the compilation steps. So you can take a look and see how it's going. Not usable yet, but I hope to have something at least compiling to Plonk very soon. So I think it will become usable soon. Yeah.
More questions? No? So, guess that's all. Thank you.